As I said yesterday in the recording, there are two methods when solving infinity over infinity and 0 over 0. In fact, another method besides just taking the highest power or to reduce and retry is to use what we call LHopitals Rule. This fancy looking picture here is of good old L'Hopital. And what he basically discovered was that if the limit as x approaches any number, and you have two separate functions, f of x over g of x, gives you infinity over infinity or 0 over 0, then what we can do is the limit actually of the functions f of x over g of x is the same as the limit of their slopes. And so what that means for us is in questions where we cannot simplify them, as we look, for example, at this first question, where we put infinity in here, and you get infinity, and you have e to the infinity, so you understand you get infinity over infinity. And maybe you're one of those that's like, I don't really buy into the whole strongest thing, or it just doesn't make sense to me. Well, the idea that L'Hopital came up with, and the fact that he could prove, was that we can actually do instead the limit as x approaches infinity, so that doesn't change, of their derivatives. So the derivative of x is 1, the derivative of e to the x is e to the x, and then retry. So now I would do the infinity in that, and I, of course, would have 1 over infinity, and so that would be 0 on the positive side, which is what you would have come up with if you had thought of the strongest function anyway, because we understand e wins. There you go. Here's another one. Sine of x over x. You plug 0 in. Sine of 0 is, of course, 0, right? And, of course, we put 0. So we have 0 over 0. But we can't simplify this, so this isn't one that we can reduce. So what we do instead is, using L'Hopital's rule, we would do the derivative of sine, and, of course, get cosine, and the derivative of the denominator, which would be 1, and then we retry. Cosine of 1, or sorry, cosine of 0 is, in fact, 1, and so we have 1 over 1. All right, let's try another one. The limit as x is approaching 0. Again, sine of 0 is 0, 2 times 0 is 0. So what we're going to do is the derivative of the top and the bottom. Now, this is not the quotient rule. This is L'Hopital's rule, which just allows me to be able to do the derivative of the top, simply cosine x, and the derivative of the bottom, and then we're going to retry. So this one would be 1/2. All right, let's look at another one. Again, we'd have 0 over 0. And yes, you could have reduced this one. But let me just show you that this does, in fact, work even for these, that you could reduce. When you do this one, you plug 3, of course, you get 0 over 0. So the derivative of the top would be 1. The derivative of the bottom would be 2x minus 3. And so now when I plug 3 in there, I'd have 1 over 3, which was the answer we got in the previous video, if you remember. All right, next one, 0 again. And again, we'd have 0 on the denominator because that'd be e to 0 or 1 minus 1. So we can't simplify it, so I'm going to do the limit as x approaches 0. Derivative of the top is 1. Derivative of the bottom, it is e to the 2x, but it's times 2. So now when I plug 0 in there, I would have 1 over 2 times e to the 0, or 1 over 2. All right, I've got some more examples over here on the right, so let's try some of these. Plug 0 in. Again, you'd have 1 minus 1 or 0, and 0 on the denominator, so we're going to do the limit. X approaches 0. Derivative of cosine is, and the denominator is 2x. Now we're going to plug 0 in there again. Negative 0 over 0. What do you think we would do here? Here I am. I've got 0 over 0. I can simplify it. There's nothing in common. Any thoughts about that? My hope is that within yourself you're thinking, wait a minute, what if that was the original question? Couldn't I just do L'Hopital's for this? Yes. The answer emphatically is yes. You can basically say, I'm going to do L'Hopital's rule again and say the limit as x approaches 0, and this time it'll be negative cosine x, because that negative stays with it, right, over 2. I try again, and I get negative 1/2, and now we're done, because it's not 0 over 0 anymore. All right, let's keep going with this. We have x squared, which would be, again, infinity over infinity. So we would do the derivative of the top. And the derivative of the top, of course, would be 2x over e to the x. But I put infinity in there. I get infinity over infinity. So what are we going to do? We're going to do L'Hopital's again. And so you get 2 over e to the x, and as you would expect, the e to the x wins in this, and so it'd be just like saying 2 over infinity, which is good. Okay, let's do this, infinity over infinity. So we do the derivative of this. We have 100x to the 99th power divided by e to the x, and we're going to plug infinity in here, and guess what you're going to get? Infinity over infinity. So we do the next one, 9900 x to the 98th power e to the x. What do you think is happening? What's going to happen? Do you really think I want to do 100 derivatives? I'd like for you to come up with that answer for that question for tomorrow's class. Thinking about, nobody wants to do 100 derivatives, so there's got to be some pattern. And I want you to think about that and somehow correlate it to good old L'Hopital's. All right, and then lastly, to finish the class here, we have limit as x is approaching infinity. When you look at this, it doesn't prompt you to think L'Hopital's. It may not even make you think about the fact that this is infinity over infinity. But when you rewrite this so that it doesn't have that negative exponent, it becomes quite obvious that once again you have e to the 2x. See, those initial rules that we learned in the very beginning about the strongest function still make a difference here. They still actually help. In fact, it's the quicker way. So I want you to do these last 2 questions and come to class with those answered for me, in hopes that you actually observe the pattern that you see here with L'Hopital's rule.